This is an activation atlas. It's a representation of how AI networks sees the world, and it gives us a rare glimpse into how it organizes what it knows in its latent space. Today, I want to explore some parallels between our brain and artificial neural networks, and experiment by trying to simulate the effect of psychedelics on AI networks. If I show you an image of a cat, your brain will be able to reconstruct the image mentally, but this mental reconstruction doesn't have the pixel values. It has some values related to the meaning of the image, what's in it, and you can understand conceptually what other things did you see that look similar to it. Now, if you take psychedelic mushrooms, this perfect reconstruction would be distorted. But because your brain encodes the image not by its pixels but by its meaning, this distortion that you will see would be quite interesting. The plan is to take what we know the brain does and try to emulate it with a neural network. Then we can take this neural network and give it some digital psychedelics to see what happens. The first thing we need to simulate is the brain's visual system, and I think the best way to do it is with an autoencoder. When we have an image and we encode this image into a latent, essentially just a list of numbers representing properties of the image, and then we decode this latent back to almost a perfect reconstruction of the original image. We use the encoder and the latent to simulate how the brain processes visual information. And the brain doesn't have a decoder because we kind of just perceive the latent and know what's the image. But the decoder is gonna help us reconstruct how it's gonna mentally look like to see this latent. And we can absolutely take an autoencoder like that and train the encoder and the decoder to try and reconstruct the image perfectly. And we will get pretty good results. But if we do it in that naive way, images that look similar are going to be really close at the latent space, even if they are images of completely different things. So in the eyes of the AI, this is going to be almost the same image, and those images are going to look to the AI as if they have nothing in common. So we need to train the encoder to produce a latent space that doesn't really encode just geometry and color, but the concept of what the image is in a similar way to our brain. And to do it, let's put the whole autoencoder concept to the side for a moment and look at a really cool model OpenAI released in 2021. And this model is of course OpenAI Clip. And essentially what this model does is it matches pieces of text with images. And it does that really well in a way that even if the image is very abstract, it shows understanding of what's in it. And the way Clip works is that if we put into it an image, let's say of a cactus, Clip would take this image and produce 512 numbers that represent this image. And if we put the word cactus into Clip, we would get the same or almost the same numbers. So it knows how to create a latent space that connects images with their semantic meaning. The problem with Clip is that those numbers only represent the semantic meaning. You can't take those numbers and recreate the image. But we can use Clip to teach our autoencoder how to look at the world a bit more semantically. Specifically, instead of having just a decoder that decodes the latent back to an image, we can have another decoder that tries to decode the latent into the Clip representation, the 512 numbers. Then we alternate between training the encoder to reconstruct the image to training it to encode a latent that can easily be converted to Clip. Essentially training the encoder to encode a latent that can both hold information about how the image actually looks like and what is the contents of the image semantically. The problem is that I want to train this network on some really high resolution images, like 1080 by 1080. And on the machines that I have, on the GPU that I have, I can't train anything even close to that. And I found some workaround that might enable me to train something like that, and I want to explain it to you. You've probably heard about Stable Diffusion before, and it's an image generation model that allows you to convert a prompt, any text, into an image, and it uses a technique called latent diffusion. It's really not important how a latent diffusion model works for this video. What is important is that for training a latent diffusion model, you first need to train an autoencoder for that model. An autoencoder like we talked at the start of the video, where we can encode an image into a latent space and then decode it back to an image. And because Stable Diffusion XL is open source, we can take the autoencoder that they used for Stable Diffusion XL, which supports 1080p images. So the SDXL autoencoder allows us to take a 1080 by 1080 image, encode it into a 128 by 128 by 4 latent, and then decode the exact image from the much smaller latent space of 128 by 128 by 4. Then, instead of autoencoding the image itself, we can autoencode the SDXL latent. So our autoencoder is essentially sandwiched between the SDXL autoencoder. So now we have a 1080 by 1080 image that we encode using the SDXL to 128 by 128 by 4. Then we use our encoder to take this 128 by 128 by 4 and encode it to a 32 by 32 by 32 latent, a much smaller one. And then we use our decoder to try to get the original 128 by 128 by 4 SDXL latent that we can then decode to the original image. And because the input size is 128 by 128 by 4 and not 1080 by 1080 by 3, we are literally saving billions of trainable parameters, going from around 4 billion parameters to just a few tens of millions, which I can train on my computer. Then we can add the clip part and train the whole network to minimize those differences, making sure the network is capable to emulate clip, but also reconstruct the actual image. Holy poo emoji. This became by far the most complicated model I ever designed. And we are only at the start of the video. And I don't know if I'm ambitious or stupid, because I realized it's gonna take a few years to train it on my MacBook. So I bought a new computer so I would be able to make this video. So after waiting a bit more than a week for it to finish downloading and encoding 350,000 images, we can start training. Before we start training the model and I'll show you the results, I want you to make a guess if A, it's gonna work really well as a representation of the human brain, or B, if it's gonna fail horribly. Place your guesses in the comments and let's see what happens. So the model has finished training and we can see that we have two images. On the left is an original image and on the right is the reconstruction of that image after going through all the different steps in the network. And so far it looks pretty good, and the reconstruction is very similar to the original image. But if you remember correctly, we don't want to just reconstruct the image, we want to make sure we do it meaningfully and that it understands what's in the image. So one thing we can do is take the average of two images latents and try to combine them to see if the combination of the two images have properties from both of them. Like in this example, we might expect to see a man sitting on a cliff with a microphone. But instead what we get is this, which is just a distorted, noisy mess. It took me quite some time to understand what's going on, but I think I figured it out and that I know how to solve it. If we take a lot of images from our training data and we plot them on a 2D plane, we get something similar to this, where each green dot represents an image that the network was trained on, and the position of the dot is correlated to the position of that image in the latent space. Now you can see that with the current training method, we get a structure that looks like a bunch of islands that are not connected to each other. And it actually makes a lot of sense for a model to learn that way, because it kind of categorizes the images. You can think about it as having an island of indoor images and island of animals, and so on. But the problem is that if we take two images and we try to get the point in the middle, we often would land on a void. And if we land on a void, it means the new point that is in the void is very far away from any image that was present in the training data. So it would look very different than any image in the training data. And that's why it looks so distorted and noisy, because it's not close to any other real image. So how do we solve this fragmented latent space? Luckily, we are not the first one to encounter this problem. In 2013, a new paper introduced the concept of variational autoencoders. And without getting too deep into the math, variational autoencoders introduce a new kind of loss called KL divergence loss, which intuitively you can think of as a force that during training pushes everything towards a more central distribution. And in this new distribution, if we choose any 2 points, in between them are a lot of samples of real images from the training data, which means the in-between image would look closer to something real. Another thing we do in the variational autoencoder, specifically to the encoder itself, is that instead of encoding each image to a certain point, we introduce some randomness, essentially blurring all the points. This helps fill in just a little bit more gaps. Now, before converting our model to be a variational autoencoder, I wanted to look at one more thing. I want to distort the actual model parameters, like scaling them, and see if even this model has the capability to produce things that look psychedelic. But after producing such distortions, we can see something pretty concerning. Not only it looks like garbage, but we can see some sort of repeating pattern. And if we count it, we can see that it's 32 by 32. Now, I don't think that's a coincidence, because our bottleneck latent is 32 by 32 by 32. And I immediately understood what's going on and what went wrong. The way our encoder reduces the dimensions from 128 by 128 to 32 by 32 is by using a convolutional neural network. Those networks repeatedly scan an image to produce a smaller image called a feature map, and then do it iteratively to produce a smaller dimensionality output. Now, one limitation this has is that the network always only sees a small patch of the image at once. This encourages the network to learn more how to represent an image by its local features rather than the global look. And because our smallest latent is 32 by 32 by 32, the network essentially learned to slice the image into 32 by 32 sections, and look at each one of them individually, and only when decoding the image understand how everything connects together. Now, also this problem we are not the first one to encounter. And this brings us to probably one of the most important papers ever published. Attention is all you need. Again, I'm not gonna dive into the math and I'll ignore most of the paper, but one of the core ideas in this paper is the self-attention. And self-attention allows us to do something very different than our current convolutional layers. Instead of relying on capturing local state, attention allows us to efficiently understand the relationship between each part of the image and each other part. This way, the network can learn to look at images beyond the local features. Currently, both the encoder and the decoder are 100% convolutional neural networks. But what we can do is to add attention layers after the convolutional networks and repeat it many times. So now that we converted our autoencoder into a variational autoencoder, and we added a attention layer to capture the global features of the image, we can start training again. And I want you to guess again in the comments if this is going to be a huge failure or this time it actually will be a good representation of the human visual system. Now, just before we start training and I'll show you the results, I just want to tell you something really quick. You might think that it's really unreachable to train models like this, that you need to be a PhD or at least have a degree. But you'll be surprised that I actually never formally learned this. I learned it online by myself. And that's why I'm really glad to introduce you guys to the sponsor of this video, Brilliant. Brilliant is an online learning platform that helps you get smarter every day, with thousands of interactive lessons in math, science, programming, data analysis, and AI. And unlike just watching video lectures, Brilliant allows you to solve hands-on problems, which is much more effective for learning. It trains you to build hands-on problem-solving skills and make learning your daily habit. No matter where you are, you can learn on the go with Brilliant. You can even learn directly about topics discussed in this video right inside Brilliant and become a smarter, more capable AI engineer. So go to brilliant.org/gallahat to get your 30-day trial, and if you come from my link, you even get 20% off on the annual subscription. Let's get back to the video. So now that the network has finished training, we can see how good it is. So let's see how good it can reconstruct this image. This is really not going well. It's really blurry, and to be honest, it's even worse than the last iteration. But even though the scope of this video really got out of control, I am not giving up. And I have a plan to take the improvements we made and actually make them work. I think the reason it came out blurry is because each time we introduced a new technique to help the network understand the image or create a more smooth latent space, we actually lowered the priority for the network to reconstruct the image perfectly. So let's assume for a moment that the network is really good now at understanding the images, but it's just not really good at recreating them. We can take some inspiration from GANs, generative adversarial networks, and do something really interesting with this network. We can create another network just beside this network, and we'll call it the discriminator. And this network would look at the output of the previous network and try to distinguish between what is the real image and what is the reconstructed one. Essentially differentiating between images that didn't go through the networks and images that did. Then we can take the network we just trained and train it to fool the discriminator. Essentially make the output images look more like the real ones. This would keep the techniques we used, but put a little bit more pressure on making the output look like real images. And honestly, I'm pretty confident it will work now. So let's give it a try and train our clip-aligned variational autoencoder transformer GAN network. Okay, the network is trained and it looks like it really fixed the problem with the blurriness, and the reconstructions look quite good. So let's try again to take two images and interpolate between them. But now, instead of giving you just one image, let's do a video of slowly going from one to the other. I don't know about you, but to me it looks really organic and really nice. Now let's do the same thing to the images we tested last time. Now, I'm sure the YouTube compression would ruin this video, so if you want to see the original one, I'll add the download link in the description. And even though I still have a lot of ideas on how to improve it, I think we can finally move to the next step and try to simulate something psychedelic with it. So let's try again to distort an image by scaling our model parameters, like we did in this image. And the new model is a lot less sensitive to those changes, and the distortions look a lot more relevant to the image. I also wanted to see what would happen if we apply this process to frames of a video. And I really don't know why, but the video came out really flickery, really sensitive to small changes in the image. And even when I tried to heavily distort simpler scenes, it still was very flickery. So scaling the model parameters and rendering a video through it is just not gonna happen. Next, I want to experiment with injecting noise into the latent space itself. Essentially taking the latent position of an image and then just drifting it around. This is to try and simulate some drifting inaccuracies that might happen in the brain when taking psychedelics. To me it looks pretty good, but I want to ask my friend for a professional opinion. Okay, what do you think? Do you think the movement looks realistic? The visuals themselves, like the distortions? How do you find it?
I think the feeling I get when I have visuals in psychedelics is where things move, but I don't really notice they're moving. I think you did that pretty good, because I can't pinpoint exactly what is moving.
Yeah.
And it gives a psychedelic vibe.
Okay.
It does look a little bit pixely. Things are changing fast in certain regions, more than other regions. I think actually the colors are pretty good. Like how the colors change a little bit.
Yeah.
They have like, they're pulsating a little bit.
Yeah.
It's I think that is pretty accurate.
Honestly, that was not by design. I don't know why it happens, actually.
It's interesting. It looks good. A lot of times I see certain patterns, recurring patterns happening in my visuals, and I don't really see them here. Like it is moving and getting distorted in different shapes, but the shapes are not organized in a certain geometry. Mm-hmm. This is what I get more in.
If you compare it to a human experience and you give it a score 1 out of 10, what number would you pick?
I think I would give it like a 6.5, maybe. A
6.5?
Something like that. Yeah.
Right.
The more I look at it, the more maybe like 6.7.
6.7.
Yeah.
Getting 0.3 more. Generous.
Yeah. Maybe if you stay like this a long time, maybe you'll get more.
Thank you, Boaz, for this call, and for anybody who doesn't know, Boaz has an amazing YouTube channel about his drawings. I also asked another friend who didn't want to be on camera, and he was a bit more optimistic. He told me it was actually very similar to the experience he had, and ended up giving it an 8.5. So far we're averaging a 7.6, which I'm pretty happy about. The noise injection method seemed to be the most effective for simulating a psychedelic experience. But I've only shown one clip to both you and my friends, and I want to show you some more clips before we finish the video. And I'm warning you, some of them will give you nightmares. Alright, so even though it's not perfect, I'm actually really happy with the results. And as much as I would love to put in just a little bit more work to make it perfect, without noticing, it's been 3 months since I started working on this video, and I just have to move on. If you would like to see more of this process and more of this network, tell me in the comments and I'll consider making part 2 where I'll try to actually make it perfect. And if you liked this video, you might also like this video where I train a new kind of LLM, an LLM with a new architecture. And also, if you find those topics interesting, consider actually trying to write some code and learning PyTorch and everything, and not just watching videos, but actually make things. Until the next one, bye bye.